Numerical analysis. Launch Saphir and start with the blank document. Click through to Step 2 and enter 75 feet for the pay zone. Accept the defaults for the other parameters. At Step 5, we decide what type of numerical model we wish to construct. The only option, which is ticked by default, is vertical anisotropy. Tick non-uniform parameters. Click Next, followed by Create. To create a numerical model, click on the Map tab in the top toolbar. We are going to create the reservoir geometry based on a top structure map. Click on the Image button and select the file map.jpg. The first task is to define the perimeter of the field. Select the Contour button and click anywhere on the edge of the reservoir image. Follow the contour, clicking to create a node at every angle. On the node, right-click to release the line. The line can be edited by moving the mouse close to the contour and clicking when the cursor changes into a pencil. The nodes are now red squares. Clicking on a red node will delete that point. If the cursor is positioned on the contour, it changes into a cross and a node can be added. An existing node can be moved by click and drag. Now to add two faults. Activate the fault icon and move the cursor to the node at the top of the map. Click when that point turns green, indicating the two lines will connect. Follow the fault line and add a node at every angle. After the last point, release the line by a right-click. Repeat for the second fault. Start at the green node from fault number 1 and after the second, right-click. The fault properties can be seen with a double-click on that fault. They can be changed by clicking on the drop-down arrow of Model. The default is a leaky fault. The leakage value may be changed from 0, which is sealing, to 1, which means no effect on the transmissibility. Note that the fault leakage value in the numerical model is different from that in the analytical. In the numerical model, the value is between 0 and 1, while in the analytical model, it may vary between 0 and infinite. Close the window by clicking OK. Next, define the map origin. Select the local XY icon, and in the map, click on the cross. It may be necessary to move the window to reveal the position of the map origin. Click OK, and observe that the map origin has been moved to our selected position. Next, look at the scale, bottom right of the map, and open the same local XY window. Select the Scale field option and click and drag a line along the map scale. Enter a value of 3,000 feet in the Scale parameter field and click OK. In addition to our local coordinates, georeference data can be handled. Refer to the help for more information. Move the tested well to the position of well P01. Double-click and the window with the well properties opens. The well type can be selected in the drop-down list. In this example, select a standard vertical well. Edit the perforations by ticking the relevant box in the top toolbar for the cross-section. Drag the top or bottom to any position. A perforation can also be added by clicking the relevant button. To get a fully perforated interval, right-click on the perforation, and the ends will snap to the top and bottom of the interval. A full explanation of the well parameters can be found in the help. Click F1 when in the Active Well window. Click OK to close the well information window. Next, we create a pressure channel as though it was a gauge. In Additional Tools, select Numerical Design. First, we are going to enter the production history of the well. Click on the History button, and in the newly opened load window, add a line and enter a duration of 100 hours and an oil rate of 200 barrels per day. Add another line with 200 hours with the 0 rate. Close with OK. Enter a reservoir permeability of 50 millidarcies. Click on the Gauge button to enter the pressure gauge properties such as resolution and noise. Select a quartz gauge and click OK, followed by Generate. There is now a pressure gauge channel called Test Design. Do an automatic extraction by pressing simultaneously the Shift key and the Extract Delta P icon. Click the numerical model icon and select Generate. There is a perfect pressure match. Rename this analysis Single Well. We are now going to use non-uniform parameters. Make a copy of this analysis and name it Non-Uniform Parameters. Check that we have the correct model options. Click on the PVT and diffusion icon and select the Numerical Modeling tab. Here, ensure that the box Non-Uniform Parameters is ticked. Close the window and select the Map option in the top toolbar. We are going to use a reservoir model with a varying net sand thickness and porosity. Select the geometry icon at the top, and in the second data row, see that the thickness is set to a constant value of 75 feet. Activate the box with the option Constant in the Thickness row. Select the drop-down arrow and Dataset. In the newly opened window, click on the plus button at the top right. Change the name of the dataset to Reservoir Thickness and ensure that the property is set to Layer Thickness. Use the Select File button. Select Load from Excel file and the file Numerical Thickness. See that the first two columns are the XY coordinates and the third the thickness value. Ensure that the units are correct and click OK. The data is now displayed in the 2D map. See the automatic interpolation method by clicking on the interpolation drop-down list. This can be changed by deselecting the automatic option. Accept the default method and click Close. A variable thickness is now being used in the model. The value in the second data row is just an arithmetic average of the loaded data. Click OK. Next, load the porosity data. Select the spatial data icon and click on the plus button at the top. Name the dataset Porosity and select Porosity for the properties. We are going to enter the new values graphically on the screen. Enter a new value of 0.2 with the icon with the pointing hand. Next, click 3 times in the southwest corner on a line from northwest to southeast. Change the porosity value to 0.15 and position 3 points in the middle of the reservoir, parallel to the first line. Finally, do the same with the value of 0.1 in the top right of the map. The value of an individual point can be changed in the table. Another option is to select one or more points with the lasso option. The color of the selected points has changed to black, and they are highlighted in the table. Clicking on the Delete icon will delete these points. In this case, we will not do that, so close the window by clicking Close. Next, return to our analysis and click on the numerical model icon. Go to the porosity value in the right-hand pane, click on the down arrow, and change the selection from Constant to the Porosity dataset. See that with the selection of the dataset, the model has added a porosity multiplier as an additional parameter in the table. Click Generate to create a match. See that the pressures from the new model are different due to the use of non-uniform parameters. Next, add an interfering producing well. Make a copy of the first analysis called Single Well and name it Interfering Well. Go to the map and select the Create a New Well icon. Click on the P02 well and a new well is added. Change the name from well number 1 to P02. Click on the Schedule tab, select the production in the target section, and click Load Rates. Next, load the pressures for that well by clicking the Load Pressures icon and selecting the text file Interfering Well Pressures.txt. Before leaving this window, select Production as the target. Go back to the analysis and load a new pressure channel. Click on the Load Pressure icon. Load from a text file, and select the file P01 Interfering Well Pressures.txt. Click through to the loading page, and after ensuring that the formats of the columns are OK, click Load. See that there is a profound impact of the interfering well on the pressure response. Select the numerical model, tick the option Include Other Wells, and click Generate. See that pressures of the tested well are not matched. There is also a new window with the pressures and rates of the interfering well. Observe that the pressures in the plot are also not matched. As a next step, change the leakage of the main fault. This is done in the Map section, but can be done in the Numerical Model section. Select Numerical Model and scroll down to the section Contour and Faults. Here, change the leakage of fault number 1 to 0.5. Click Generate and see the improvement in the match. If the data is very good and stable, try to optimize the match. Go to Improve and select the leakage of fault 1 as a regression parameter and run. Because the data is of high quality, we get an optimized match with the leakage value of 0.2. Next, introduce regions with different properties. Create a copy of the first analysis and name it Gas Cap. Go to the map and activate fault number 1. Next, pick the southern end and extend the fault until it intersects the contour. In this model, assume that the section on the left is the gas cap and the well is in the oil. So, the fault number 1 is not a fault, but is effectively a boundary between two regions with different properties. Double-click on fault number 1 and change the flow model to Composite Limit. See that the leakage has changed from 0 to 1. Click OK. Next, select the region icon and click anywhere in the gas cap region. Double-click on the Region 1 anchor and rename it to Gas Cap. Click OK and return to the analysis. Select Numerical Model and scroll down to the section called Gas Cap. Enter the values for the mobility and diffusivity. Refer to the help for definitions of these parameters. In this case with the gas cap, select a value of 0.2 for M and leave D as 1 and click Generate. Observe the impact of the gas. The derivative does not change that much, but the overall depletion in the history plot is a lot less. The impact of the gas cap can be seen better by extending the buildup. Do that in the numerical model. Select Time Stepping and change the value in Simulate Until from 300 to 2000 hours and click Generate. Now the impact of the gas cap can be seen clearly. Click on the numerical model icon. In this case, the region values typical for a gas cap were used. Likewise, values for an aquifer may be used by changing the appropriate values for the mobility and the diffusivity. We recommend first calculating the expected values for these parameters and using these as starting points. Also, note that at the top of the parameter list, it is possible to select either mobility or diffusivity, or if we deselect that option, to enter values for porosity and permeability. This is applicable for a reservoir with changing properties, but will not capture the change in PVT properties as found in a gas cap. Exit the numerical model. We now come to the last section, a change of tested well and radial composite modeling with the water injector. Create a copy of the first analysis and name it Injector. Go to the map. Select the new well icon and click at the position of well I02. Change the name to I02 and go to the schedule. Ensure the target is set to pressures and click Load Pressures. Select a text file as a data source and the file injectorpressures.txt. Click Next, check the format of the columns and click Load. In the pop-up window, select Skip the new data, Apply to All, and OK. Next, Load Rates. Select the text file, injectorrates.txt, load the data, and click OK. Note that the injection rates are defined as negative. The rates are defined as oil rates. This is because we cannot change the fluid from oil to water in an existing analysis. The only way is to make a completely new and empty analysis, but then we would lose the model. However, in this case, we can change the 3 basic fluid PVT parameters to those for water. Go to Analysis, select the PVT and diffusion icon, and in the Analytical Modeling tab, we could change the formation volume factor, viscosity, and total compressibility from oil to water. But we will keep our default parameter values here, so exit this window with Cancel. Click on the information icon at the top and change the reference well to I02. Next, do an automatic extract pressures. Use the same numerical model as in the single well case. Go to the numerical model and click Generate. Observe that the early and middle time does not match, but the late time looks okay. The derivative shape is indicative of a radial composite model, which is quite typical for water injectors. Logically, the water-swept area around the well has different dynamic properties to that of the reservoir proper. Go to the Map section and activate the injector well. Tick the radial composite box. In the table, see that the composite radius is, by default, 300 feet. Click OK, and in the map, zoom in on the injector well. Click on the region icon and place an anchor close to the well. Double-click on the anchor and name it Injected Area. Note that in the numerical model, we can select any region to be the reference region. In the analytical model, the default region is always the area in direct contact with the well, so the composite values can differ between the analytical and numerical models depending which regions are defined as default. Go back to our analysis, the numerical model, and enter a value of 2 for the mobility and diffusivity. Reduce the wellbore storage by a factor of 10. Click Generate. Observe that the initial stabilization is too low, but the radius looks to be okay. To get a best match is often a matter of trial and error, depending on the quality of the data. In this case, do an improve and select the M and D as variables. After the optimization, the M and D should be close to 3. This concludes this session on numerical analysis.